Well, good morning, and let's give it another try, shall we? Who touched the thing? Someone did it. Someone did touch it. Well, anyway, today it's much brighter than yesterday. Right here. Oops, where is it? Here. In the middle of the shadow, that bright dot, which can't be explained by particle theory of light, except if those particles are photons, because photons are microscopic particles. And microscopic particles behave very, very differently from macroscopic particles. They obey different set of laws. The trajectory for a microscopic particle isn't defined by Newton's law. The same particle in the same conditions might travel using different paths. You should have it. So, one of the very important features of quantum world is this. If we have a ball on a string, it can have any possible energies. It can have any possible trajectories with any possible radius, but in quantum world, actually, the most of values are restricted. Only certain values are allowed, and the very first model which mathematically described that fact was the Bohr model of hydrogen atom, and with a little algebra, actually very little algebra, we can derive all these expressions and more for everything. Linear momentum, angular momentum, radius of trajectory, total energy of the atom. What about other energies? Of course, they all will be quantized. For all energies and other variables, we will have only a certain set of allowed, not restricted values, and we can even calculate all of them. We know 3.14, 9 times 10 to the 9th, 9 times 10 to the negative 31st, 1.6 times 10 to the negative 19, 6.6 times 10 to the negative 34, converted into electron volts, and just plug any number from 1 technically to infinity, and you can get all values for all allowed available energies. People in physics call them levels. They imagining an electron sitting, again, that's slang, on a certain level, and that electron can jump up or down. That jump, of course, changes the energy of the atom. And electron volt is much more convenient unit to use for energies than joules, because numbers are simple. Negative 13.6 electron volts, that's the lowest possible energy level. The next is negative 3.4, negative 1.51, etc., etc. And that is completely sufficient now to answer these two questions. Now this area is allowed. See? That was quantum world, and now it's a classical world. And all we need to do is just point a finger at the equation you want to use and use it. And using in physics means writing it down, plugging in a value of a specific variable and looking at it. That's it. Let's see if Webassign is acting as it's supposed to be acting. So I don't have much space here, but I think the pattern is clear. This number in the denominator of this fraction is equal to the number of the answer you want to choose. And here, this number, a multiple, is equal to the number of the answer you want to choose. That's number 2. And that's number 3. All right. So the nth energy level is not described by this equation. Yeah. What's missing? Square. That's it. That's thing to remember. So when n equals 2, n squared is equal to 4. That's it. And the next question, which is the third, is related to a term which you may have heard or may have not heard, ionization. If you have heard, you know what it is. If you haven't heard, you should ask a question. If you're not asking a question, I assume you have heard it and you know what it means, right? What does it mean? Ionization, yeah. To lose an electron. In this situation, it's a hydrogen atom. It has only one electron, so it loses it. But loses, what does it mean? It means it has to gain some energy enough to fly away from the proton which holds it. And it's a very similar situation to calculating the speed a satellite needs to reach in order to fly away from the central mass, from the Earth, for example. And in this situation, well, the maximum energy required, the minimum energy required for that is negative 13.6. The maximum is not set. Yeah. Any energy above that value, how do I know? Well, electron in the first state has this particular amount of energy. We call it the ground state. It's grounded forever. And if a photon which collides with electron has amount of energy less than that, a photon also has some energy. Let's say it's less than this. In that case, the new, we can call it final energy of an electron could have been equal to the initial plus the energy of the photon, which is just a straightforward application of a law of conservation of energy And that would give still some negative number. So the electron would still be inside the atom. So, oops, 13.6 electron volts is sufficient to bring it outside. More electron volts would sufficient to even make it move faster away from it. And this type of reasoning might be helpful to see the difference between just ionization and the photoelectric effect. Technically, this atom can be, well, first of all, hydrogen normally is gaseous, but under very low temperatures and very, very high pressure, we can make it solid. So kind of like a metal plate. And actually, people think it could have been superconductor. And even if an electron being moved away from a proton far enough, it still might be left inside of that particular, well, piece of solid hydrogen. So if we want to move it outside, we need to do two kind of things. First, we need to ionize that atom, but the electron still might be wandering inside of that metal plate, and so we have to have some extra energy to move it outside of that plate, and then photoelectric effect is happening. Now, what do you think about this question? Let's say we shine on hydrogen with the light. We can calculate the wavelength. Yeah, the wavelength equals actually 1240 divided by energy in electron volts. So very short wavelength. Doesn't matter at this point. What's going to happen if that photon collides? What do you think might happen with absolute certainty? Yeah, the key word is definitely. And again, now you have to do some little calculation. A hydrogen atom is in the ground state. That immediately tells us the energy, negative 13.6 electron volts. And of course, what we want to do is this. The new energy this is the calculation you have to finish and look at the number. And then after looking at that number for about like 15 seconds, you should make your mind and choose the answer. So negative 13.6 plus 10. Equals we already start having 50-50 distribution. That means this is a good question. Makes you think, makes you wonder. Well, not you. You sit your mind. So negative 13.6 plus 10. What should I write? Now what should we do? We should look at the allowed energies. at the set of allowed energies. Not that's a specific feature of a quantum world. Not all possible numbers are allowed to be physically realized. So negative 13.6 is allowed, not restricted. Negative 3.4 is allowed, not restricted. Negative 1.51 is allowed, not restricted. Negative 3.6. That might mean I have no idea, or not allowed, you have to say. Not allowed. How do we know? We can see negative 3.6 falls between negative 3.4 and negative 1.5. And all numbers between those allowed are restricted. That's how the quantum world works. So we can calculate a number, but it doesn't mean it makes any sense. So the answer is no. So quantum world is very similar to human world. Lots of things are restricted. Well, next problems slightly different. Now we know that a photon is being absorbed. Yeah, disappeared means absorption happened, did happen, and we know that during this process, the atom changed the energy from the ground state to the third one. Well, that information is completely sufficient now to figure out the wavelength or frequency of that photon. But first, let us take a look so I could close it. This app is a model of what might be happening. So that's an electron, proton, electron. Those are photons in different wavelength, different color. So if a photon collides with an electron jumps. Of course, it's not happening inside. Yeah, this is just a model. Even trajectories don't exist in reality, not circles, just clouds of probability. But anyway, so this is a good model which explains, for example, the linear spectrum of hydrogen or any other element, and the collision leads to a change in the energy, but it can't stay excited forever, and eventually collide. All right. Eventually, it jumps back, and when it jumps back, what's happening? It emits a photon. So, using the law of conservation of energy, we can relate these processes very easily. Right? So, here we have energy number one, which is ground state energy, negative 13.6 electron volts, and we have energy. Now, you got to confuse yourself anyway, because you can write new, final, 2, 3. It's your choice. It's a second energy in this experiment, but it's a third energy level. So what do you write? A 2, or a 3, or final, or new? I choose 3, because this is a number which people usually use to number the states. We know it's supposed to be squared, and the energy of the photon absorbed or emitted always equal to the difference. Yes? That's 13. Well, technically it should be final minus initial, so 9 over 1. And that's 8 over 9, 13.6 electron volts, right? 9. And I don't know, what number is it? Now, again, a standard disclaimer. If I made a mistake, I did it on purpose. Point 1. This is an exercise in using negative numbers, subtracting negative numbers. Minus and minus makes it positive. So, and the wavelength, well, we know we always can convert electron volt in joules and then apply, let's write it one more time, relationships. Energy of a photon is related to the frequency, and frequency and wavelength are related to the speed of light, but we have it used, and now we have a shortcut which you don't have to use, but it saves time. 1240 over 12.1, about 102.5, that will be nanometers. Any questions? Well, so we know that when not just hydrogen atom, any atom changes energy from high to low, that results in normally. There are all the less probable events, but the most probable event, it emits a photon of light, and that light travels away, and we can actually see the spectrum. We will in a minute. First, let's do one more specific problem. An electron, see, drops, in quotes. Of course, no one drops an electron. It just changes energy from a high to low. And now the initial, why do you, oops, weird. Okay. Now the initial energy is supposed to be equal to the energy of the second level, which is negative 13.6 over 4 electron volts. And the final energy will be equal to the ground state energy, which is negative 13.6 electron volts. And the energy of the emitted photon supposed to be equal to the difference. And the wavelength again will be equal to 1240 over this energy. I heard you clicking, so what's the number?
120.
Well, for the wavelength. Can you say again, please? I just 121.6. Yes, sounds reasonable. Nanometers. That's not in a visible spectrum. We know the visible spectrum is between 400 and 700. This is ultraviolet, very, very short wavelength light. And yeah, I had 5. Well, let's take a look at this. That's why you need this thing. You know what a diffraction grating does to light. It makes a spectrum. Yeah? It makes a rainbow out of it. Now let me just shut the lights, so because now a lot of ambient light. That's it. This tube actually, yeah, classical hydrogen. But of course, if you look straight ahead, you will not see anything, because straight ahead we will have to see central maximum, which is white. So you have to search for the first maximum. So you have to look slightly to the left or to the right, and well, we have to have the right orientation. So you really have to look at it. And if you look, so you can see the continuous spectrum, because that bulb, the regular bulb, the filament, provides light with all possible wavelengths. But if you look to the left, when I look to the left, I can see violet, blue, red line, and a lot of space with no light between. So at the top we have the continuous spectrum, and below that, when we look, so the angle is about this. You should try to look. You can see lines, a linear spectrum. Where's your? You don't have it. Where else would you see a linear spectrum? So clearly at least 3 bright lines and some extras in between. Yeah, even, yeah. So violet, blue, and red. And people have seen these type of spectrum way before the Bohr's model have been published. But they just couldn't explain. They couldn't explain. They have measured all the wavelengths. They even figure out how to calculate those values purely from the numbers they've measured. But they couldn't explain why did it work. So this was, you know, this equation with a fixed number about 1 times 10 to the negative 7 has a name, Rydberg equation, Rydberg constant. He just was playing with numbers and found out that for hydrogen, every wavelength can be found using this equation. But why? He couldn't explain. Those are people who observed and described certain lines they have seen in the spectrum, ultraviolet, visible, infrared, but again, they couldn't explain the reason for those specific values for wavelength they've measured. But the Bohr's model gives explanation with very simple algebra, plus it actually allows to calculate that constant, and it gave a very accurate very accurate value for this constant. All we have to do is just apply the law of conservation of energy and solve it for the wavelength, and that's it. That was a triumph of, well, the first solution of a really quantum problem. So the lines you saw, they belong to so-called Balmer series. It happens when an electron ends on a second level. If electron drops to the ground level, the energy change is so large that photons have very high frequencies, very short wavelength, and it doesn't belong to a visible spectrum. It belongs to ultraviolet part of a spectrum. If electron ends on the third level, again, that is outside of a visible spectrum, that's infrared. But if electron ends on a second level, that's when red, blue, yellow lines of a visible spectrum appear. And the question is, let's say an electron initially is in a third state. How many different photons can be emitted? So that's a counting problem. How many different options? Well, if it starts from the third, it can drop, well, to only levels below the third. So how many levels do we have below the third? 2. But if you answer 2, that would be wrong. Because the question is not about levels, the question is about changes between levels and about the number of photons. So in this situation, this is one possible photon. This is another possible photon. But also, if an electron dropped from third to second, after that, eventually it has to drop from second to third. And that will be the third possible photon. That's it, a counting problem. 3. Well, and in general, if we have not a hydrogen atom, but any other element, and if we strip off all electrons but one, we can apply the same mathematics and calculate the same energies, but we just need to take into account the number of protons, because Coulomb's force depends on that. Unfortunately, real atoms have more electrons than one, and unfortunately, this theory doesn't work for real atoms, because electrons interact. That interaction is strong, and because of that, people eventually have invented quantum mechanics, Schrödinger equation, to calculate all possible energies for all possible elements and molecules. And if we look deeper into the atom, we see a nucleus, and you know from chemistry, every nucleus has a specific structure. It has a certain number of protons and neutrons. Neutrons are neutral particles. And a standard chemical symbol has 2 numbers usually, or 1 at least, the top. The bottom number tells the location of the element in the periodic table, and it also is equal to the number of protons, and it also is equal to the number of electrons for a neutral atom. And the top number tells us how many particles are inside together, neutrons and protons, or people use one word, nucleons. And people sometimes get confused in the names. This is, we call an atomic number, and this is an atomic mass number. One word, big difference. An atomic number, again, the number of protons. An atomic mass number is total number of nucleons. And for each element, we can now find all information available about it. You know, every element usually has some isotopes, and an isotope should have exactly the same number of protons, but a different number of neutrons. For example, very important element like carbon has also many isotopes. Some of those isotopes are stable, some not. And this question is about a specific, very important isotope of carbon. It's unstable, it decays. It takes a long time, but it decays. So carbon-14, how many neutrons does it have? How many neutrons does the isotope of carbon-14 have? Oh, we have two, yeah. Again, it's a problem about just straightforward application of a definition. Yeah, that's it. So what did you say? "14" means this number is 14, this number is 14. C, well, there is a missing number right here. We don't see it, but we always can figure it out using the periodic table. We just have to look at it. 6. So we can add it. That's this number. This is the number we are looking for, the number of neutrons. 14 minus 6, 8. Yeah. Now, unfortunately, again, if we use international system of units for everything we measure, numbers are ridiculously counterintuitive. We have no idea what it means. Negative 31st, 27th, and when we talk about energy, we have invented a new unit, electron volts. Now, when we talk about masses, we also need a new unit, and that unit has been invented. This is an official definition of atomic mass unit. Atomic mass unit is equal to the mass of 1/12 part of atom, carbon-12. So to get the atomic mass unit in kilograms, what we need to do, we have to weigh the mass of a single carbon-12 atom, and then take that number and divide by 12. According to this definition, that will give us atomic mass unit, or people just use AU. And now we have a conversion factor between kilograms and atomic mass units. And now numbers are kind of more reasonable. Yeah. Atomic mass unit, of course. The mass of a neutron, the mass of a proton are very close, not equal. And these digits matter if you need to solve a problem on a Webassign or at home. Yeah. You got to carry all the digits, because if you round them up, there will be no difference at all between the atomic mass unit, between the mass of a proton, between the mass of the neutron. Important. And as we know, an electron is about 2,000 times lighter than a proton. And now, So and actually I can change this number to any number. I think the isotopes of carbon start from like 9 to where is it? It was here somewhere here. From 8 to 22, actually. From 8 to 22. As this question is not about the structure of a nucleus, right? This question is about the atom with that particular nucleus. What do they all have in common, all those nuclei? The number of neutrons might be different, but it's carbon. It is still carbon. So the number of protons has to be equal to 6. And a neutral atom also always should have also the same number of electrons. So 6. Well, 2 more questions. Today I want to reach the record number of questions. I believe the set of answers is the same. Bless you. But the questions are different. One is about atom, second is about the nucleus of that atom. And the difference is very, very important when we start calculating things related to the structure of a nucleus. So, for a carbon-12 atom, what should be atomic mass equal to? What do you say? 12. Because 1 atomic unit is 1/12 of that. So if you have 12 atomic units, that should be 12. That's, well, just a straightforward application of a definition. But what about, so 12. What about the nucleus? Well, what's the difference between atom and the nucleus of that atom? Electrons. Yep. So the mass of a nucleus should be equal to the atomic mass, the mass of the atom, minus, well, how many electron masses should we subtract? For the carbon, how many electron masses should we subtract? 6. 6 electron masses. And that's important because if you read numbers in the periodic table, those are atomic masses. So we know all atomic masses. But for all calculations related to nuclear reactions, nucleus, we have to use nuclear masses. And people forget that difference very often. Well, so the answers. Now, of course, now we have to relate these 2 new units, 1 unit for energy, another unit for mass. We need a new conversion factor because it allows save a lot of time for calculating energies on a microscopic level when we know atomic masses of elements. So, what do we do? Well, we can start from using international system of units, but in the end we have to make a conversion. 1 atomic unit in kilograms equals 1.660540 times 10 to the negative 27 kilograms, and the speed of light is actually close to 8.99 times 10 to the 8th meters per second, and we have to square it, and that will give us joules. And 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So 1 joule is equal to 1 electron volt divided by 1.6 times 10 to the negative 19. Right? That's joules. So finish it at home. It's a good exercise. That's the conversion factor. The energy stored in one atomic unit is equal to 931.5 million mega electron volts. That's it. So now we can use this conversion factor for calculating energy related to any mass measured in atomic mass units, just by multiplying 931.5 and the mass in atomic mass units. So this is the summary. There is not much of physics here, just converting units. And one more question. Ten. I just realized. Yeah, that's a question number 10. And that is official record for the whole course, 10 questions. I can retire now. Well, electrostatic, no. Protons repel each other, right? And protons are so close that repulsion is very, very strong, Coulomb's repulsion. And protons are very light. So gravitational force is so weak, they repel each other much stronger. So gravitation can't hold them together. And none other of forces can be responsible for the existence of a nucleus. And that force must be so strong to overcome Coulomb's repulsion. So people named it strong. That's an official name of this force, a strong nuclear force. But we don't feel it because it is strong only when subatomic particles very, very close to each other. It rapidly decreases with distance. So in the real world, that force doesn't make any difference. We can't feel it, we can't measure it much. Gravitational and electrostatic force will be much stronger for us. But that force does exist because without that force we wouldn't exist. Atoms wouldn't exist. And it means if we want to build up a nucleus, some energy has to be spent. If we need to break it apart, some work has to be done. And that amount of work has a name, the binding energy. So if we take a nucleus and we start moving away protons and neutrons one by one, and we calculate how much energy has been used to do that work, that amount of energy has a name, binding energy. That energy binds the particles due to strong force. And it turns out, if we measure masses, the mass of an actual nucleus, and if we measure individual masses of protons and neutrons, which we need to put together to create that nucleus, we will get different number. The total mass of individual nucleons is always slightly greater than the actual mass of a nucleus. And Einstein told us why, because energy and mass are related by the Einstein equation. That mass difference, or people call it mass defect or mass deficit, If we measure it in kilograms and multiply by speed squared, we'll give the binding energy in joules. But now we have a much faster way for calculating energy. We can measure mass defect, mass deficit in atomic mass units and multiply by 931.5. That will give the amount of energy in mega electron volts. That's it. That's a question number 11. This is a short memory test question. Yep, because the answer to this question has been presented several minutes ago. We just have to represent it again. If we look at the numbers in the atomic, in the periodic table, these numbers, 99, 152, 87, those are Z's, yeah, the number of protons. And numbers with decimals usually represent atomic masses, not nuclear. So how do we use periodic table to calculate binding energy if we need it? First, according to a definition of mass defect, it should be a difference between total mass of individual nucleons and the actual mass of a nucleus. So what does it mean? It means, how do we calculate the total mass of individual nucleons? Well, we know each element has Z protons. So Z times the number of protons. Plus, we know each element has a certain number of neutrons. So, times the mass of a proton, mass of an individual proton. Now, how do we calculate the number of neutrons? That's the difference between atomic mass number and atomic number times the mass of a single individual neutron. And that's supposed to be the mass of a nucleus. But we don't know this number normally. We know atomic mass. So how do we go about that? Well, in mathematics, there is a rule which is simple but convenient. If we add and subtract the same number, that doesn't make any difference. What number do we want to add and then subtract? Total mass of the electrons. How many electrons does it have? Z electrons. Because the number of electrons is equal to the number of protons. So, electron mass. And now this together can be combined. So Z times the mass of a proton. Number of neutrons times the mass of a neutron. Plus same Z times the mass of electron minus the nuclear mass, the mass of a nucleus, total mass of the electrons, and that's what is atomic mass. This is the number which we can read in a periodic table or Google. If you enter like the mass of iron atom. That's what will come up, atomic mass. Well, that's the most important part of a calculation. If we know the mass defect, we can just multiply by 931.5. That will give the binding energy in mega electron volts. All we need is just an example. Carbon-12, the most important, one of the most important elements for humans. Our life is based on carbon, oxygen, hydrogen, a little bit nitrogen. So, carbon-12, oops. How do we write the symbol? 12 is atomic mass number, and Z equals, so that's A, Z equals to 6, right? All right, so delta M six times the mass of a single proton, 1.007276. And remember, we must keep all the digits, otherwise there will be no difference. Plus, how many protons? 6. How many neutrons? 12 minus 6. What is the mass of a neutron? Times 0.00866. Interestingly enough, a neutron is slightly more massive, heavier than a proton. A proton is stable. People search for a proton decay, but couldn't find so far. Neutron is unstable. It decays into a proton and electron. So it kind of, maybe it has a proton and electron side. We don't know. Now, 6 electron masses. And now we need to subtract. So this sum represents the sum of the masses of individual particles. Now we have to subtract the mass of atom, carbon-12. So what number should I write here? Those are, of course, not kilograms. You know, a kilogram would involve 10 to the negative 27 or something. Those are atomic mass units. So what number should we write for the atomic mass for carbon-12? That is correct. We have answered this question again several minutes ago. So this number is equal to 12. Now you have to take a calculator and calculate the difference. And that will be the difference. It is a relatively small number for us, 0.09, etc., etc. So if you add all those, that gives you 12, 0.098. You subtract 12. That's mass defect for carbon-12. How do we calculate binding energy? We multiply by 931.5. But in physics, there is a chart for binding energy per nucleon. It's basically energy density for different elements. With different elements, we have different number of nucleons inside, so binding energy per nucleon changes. And how does it change? Well, Of course, we know how. It has this graph for the binding energy per nucleon has a peak. This peak shows the most stable elements in the whole universe. So there's a theory that eventually everything becomes just lead or iron. Elements on the right end of this graph have no stable elements. They all decay. Uranium, plutonium. So there is a critical element somewhere here. Above that number, no stable isotopes exist. Below exist stable isotopes. And the difference is in size of the nucleus. Yeah. If a nucleus is relatively small, the force of nuclear attraction can hold all particles together forever. But if the nucleus is large, because force of attraction decreases rapidly with distance, but much faster decreases than Coulomb's force. Coulomb's repulsion eventually wins over strong nuclear attraction, and large elements just can't be stable. They decay eventually. So you can, of course, look it up. There is that element which divides the whole periodic table into two parts. One part of elements which have no stable isotopes and elements which have. And, well, if we have to, well, now we have to study properties of unstable elements. Stable elements are just stable. They exist forever. A decay means it can't exist forever. Eventually, that nucleus, well, explodes, split in smaller parts. That's what it means. And, well, how can we describe that mathematically? Of course, we start from a certain amount of radioactive material. How many? I don't know, this many. That's the initial number of radioactive atoms in that particular sample of radioactive material. And they decay. So if we wait long enough, of course, we should have less atoms of the same material left inside this sample. Well, first of all, the first confusion happens when people think that the mass of the sample changes drastically. No. A decay means that you had one large atom and then you have two smaller, but most of them actually remain inside that physical sample. So some particles travel away due to, well, through the surface, but the most 99.99999% remains inside. So we don't talk about changing in the mass of the sample. Inside this sample, we still have almost the same amount of material, but that material now is different. Yeah. Some is the same as before, some is different. This is, of course, what we need to describe, how much is left of the same material. Well, first, a single action of a decay happens, and we can measure how many decays happening per second. The number of decays per second, that's what we call radioactivity or just activity. Activity. The number of decays per second. The number of decays, the number of decays. That's what it can measure actually, easier than the number of actual atoms. And activity, of course, is related to the number of elements. If we have many, many radioactive atoms, we have high activity. If we have just a few, we have low activity. This coefficient is not a wavelength. We use the same letter, lambda, but now it's called a decay constant. Is measured for all important materials. And well, how would we write? Well, that's the magnitude of it. Yeah. How would we write the rate of change of the radioactive atoms? Mathematically, that would be change in the number over time. And because the number of atoms decreases in time, the rate of change, which is slope, is actually negative. So, but the graphs for both are equal in shape. Yeah. The number of atoms, number 1, 2, 3 is always positive. So if this number decreases in time, this number also decreases in time. This is just a fixed coefficient. And turns out, if we solve this equation, this is an equation. That can be solved mathematically. The decay happens exponentially. The number of atoms decreases exponentially in time. But we almost never ever will have to use this equation. I need to point it at that equation, but there's a much easier way to describe a radioactive decay, which is this. This model shows what is happening to the number of radioactive elements. You see, we have less and less red dots in time. What's happening? Well, red dots represent some radioactive element, plutonium. It decays, and instead of a plutonium, we have something different, black dots, and we can count the number of dots. We need to count the number of red dots, but of course, if we know the initial number and if we know the number after a certain time, we can also calculate the number of decayed. How many did decay? That would be the number of black dots. That would be the difference between these two numbers. But it is, oops, I close it. It is clear from a fairly logical point of view or from this applet, it has to be a certain time. If we wait, if we wait that amount of time, we should have left exactly a half of the initial material. See? Almost. For me, it's hard to find that instant, but if we wait long enough, we should have left exactly a half of the initial number. But of course, this new number becomes initial for the next same interval. If we wait exactly the same time, one more time, eventually we should have left exactly a half of the previous, which will be a quarter of the initial. And that is the best way to describe the radioactive decay mathematically. Okay, so we've reached a quarter of the initial, a half of the previous. So how would we describe it mathematically? Well, that should be our graph. We start from certain initial value of radioactive elements. We wait a specific time interval, which is measured for all materials, has a name, half-life, half. So by definition of this time interval, if we wait, we should get left exactly a half of the initial. But if we wait exactly same, so this is what we call, that's another one, half-life. So that's going to be 2. And that's not a period, even the letter is similar. So right here we should have the initial of the previous. So this value should be equal to 1/2 of the previous. If we wait one more half-life, eventually we should get what? We should get 1/2 of the previous. And now you see the pattern, of course, right? So this is how we can write the law. Or shortly this, where this variable n represents the number of half-lives. Basically, this is what it is. This is the total time interval from 0 to a certain instant. If we divide it by this number, we get, in general, it doesn't even have to be a whole number. In general, in mathematics, this equation can be written like this. And there is a mathematical way to rewrite it like this. Why? Wrong location. To rewrite it like this. Which means these variables must be related. So if you're confident with logarithms, you can derive that relationship. Well, so again, the summary, readable. The law of radioactive decay in the most general form. This is not half-life. This is lifetime, a different name. But we wouldn't probably ever use this equation. We would use, well, okay, that's a definition of activity, an official definition. And I forgot to mention the number of decays per second. That's what we call a becquerel or BQ. And this is how activity also changes. And this is a note. There's a difference between the mass of that radioactive material and the mass of the sample which has it inside. The mass of the sample practically doesn't change. And that's not a question I want to ask. I already have reached my limit, I think. But this is just a mathematical exercise. The black line represents the radioactive decay of a certain material. Now, if we take a look at red and blue and compare with black, which graph represents faster decay? Of course, red one. Here, it reaches faster a half of the initial amount. And this graph represents a slower, it takes more time to reach the same amount. That's it. So faster decay means time related to this decay is smaller, which means decay constant is larger. Slower decay means longer time, smaller decay constant. But again, we wouldn't use this type of equation because we would use this type of equation. It's much easier to just count the number of half-lives. 1, 2, 3, and just raise a number 2 to the power of the number of half-lives. Probably, what is an official definition of lifetime of this variable? This is how much time should we wait, so we would have left 1/th, not 1 second, but 1/e of the initial material. That's it. Another slide which tells us how to algebraically relate these variables. We just have to do some algebra relating exponents and logarithms. And this expression tells us how, if we want to, how can we relate these variables: half-life, lifetime. We just have to use a logarithm of 2, which is 0.69, I think, about 0.7. And now we know everything about the radioactive decay. Everything we need to know, let's say. Yeah. Not everything. No one knows everything about everything. This is an example of different half-lives for different materials. Some live a fraction of a second. Some might live billions and millions of years. What does it mean, actually? It doesn't mean that if I take a single carbon-14 atom and place it, and I look at it, in exactly 5.73 times, well, 10 to the third years, it's split. No. We need to understand that that's not the case. These are just averages. We can't never ever predict when that particular atom will decay. But if we have many, many of them, we can say on average that if we wait 1 half-life, on average, practically a half will decay and practically a half will remain. Well, now, this is a device which has been invented to measure radioactivity, PQs or Curies initially. Geiger counter. It's counting right now particles traveling through this area. And we have to go really, really, really deep in the Earth to escape any particles traveling through us. Cosmic particles, they always travel, they reach, we've been hit. And one of the results of that, mutations. And so, come on. Okay, one more particle. But now, can you hear it? This is how many particles now traveling through this area, and it can count the number of particles per second, and that's what radioactivity is. Now, this clearly is radioactive. Why? Well, people used to use this type of a paint, and it's red because it has uranium in it, and people used to eat from that. Hopefully not anymore. And there is another very commonly used device which has the radioactive elements inside it, smoke detector. If you open it, there is a radioactive source of beta particles. Doesn't matter what particles are, but the good thing about this is that different particles have different energy, and some particles actually can't penetrate even like thin piece of paper. And see, an actual doesn't give you anything. But for some particles, really, still, for some particles, we really need to have something very thick and heavy, like a piece of lead, to prevent them from getting through. So that's dangerous. I have to wash my hands. You can buy a pocket Geiger counter, actually, and have it with you and measure radioactivity where you are, and there is always certain radioactive background even in this room. So unfortunately, well, it's unescapable, but yeah, sometimes mutations are good, sometimes mutations are bad. So we wouldn't be here without mutations. Okay, that's not a question. Actually, how many questions do I have? How many? 14. I want to ask this question. I want to ask this question. 8, 9, 10, 11. That's going to be question 12. You have 4 minutes to solve this problem. This is the last slide for today, I promise. It is a counting problem. So we take from, I don't know, a certain storage, certain radioactive material, and we are very, very quick to count how many radioactive atoms are inside that sample. Turns out 128. This is what is being called now T equals 0. Of course, the number of radioactive elements decreases in time. And we know from this particular description that if we wait 1 hour, we've got left 64 of those. So this is 1 hour. According to a definition, the time we need to wait until the half of the initial number of elements decays and half remains has a name. Yeah. That's what it is. This is a half-life of this particular material. We actually can write it down. 1 hour. We actually can set up an equation if we want to. N should be equal to the initial divided by. So we can set time, for example, to any number of hours. If we wait an extra hour, so if we wait 2 hours, that's how many original atoms should left. This is how many in the next hour, in the next hour, in the next hour, in the next hour, in the next hour. So 1, 2, 3. Ignore it. I said it to myself. So in 7 hours, 1 atom would left. That's what it is, what it says. But that atom eventually should decay, because they all should decay on average in 1 more hour. So that's how many hours should be spent, waited. Any questions? Well, finish the homework, please. Hopefully today. So you would have a couple of days to review everything. You don't have to, but that's best approach. Well, thank you. Good morning.